I remember one of the first entities that we looked at, we actually, to quickly jumpstart, we looked at acquiring existing entities. For example, one of the entities that we went and looked at was a company called Project Spokane, running out of Missoula, Montana. And there I met a few other guys, one who many in the mining industry would know, Kevin Zhang, who's the SVP at Foundry. He was one of the ones behind that site. And he later moved on. He had some disagreements with management and he moved on to work at Greenwich and then Foundry. There were a few others. Some of the guys like at Hash House were also connected to that. And then we looked at other sites, at least starting out as in acquiring. Going back to that site, I think at that time, this was October 2017, they were running about 20 megawatts. And they built this on a very low, almost like a shoestring budget. It was a very interesting site to see. Speaking of Genesis too, we ended up investing in a company. When I say we, I mean SBI Group. It was done through another SBI Group company into a data center company out of Europe who we partnered with to build data centers in Iceland. And they ended up also in that process acquiring a very small Icelandic entity. And we built a data center within like a stone's throw of Genesis data center just outside of Keflavik, or actually in Keflavik, just outside of Reykjavik. And we built in northern Iceland. So it definitely expanded a lot. And in that time, 250 megawatts was definitely a lot larger than it is today. And through that process, we learned several mistakes along the way. I mean, we made those mistakes. We learned from them. I learned from them. And I'm still like taking what I learned and
what are some mistakes that come to mind?
So some of the mistakes too is in just how some are contractual, some of the engineering design, some in being careful of like how the power infrastructure is done. I mean, there's several that just, there's a lot when you go through this size and you go through several procedures. Some are large mistakes, some are small. And no matter how small it is, even for a successful operation, there is always something that can go wrong and something that will go wrong, no matter how successful operation is. And each one of those points turns into a learning opportunity. And that's what we were able to capitalize on. And that's definitely what I've taken to heart and continued to take into the future.
And as you mentioned, every infrastructure project is always not on time. It's really hard to get them on time, especially if it's your first one of that scale.
Yes.
And we're talking about managing tens of thousands of units. So did you guys develop internal tools to do that? Were you relying on third-party tools? And what operational knowledge maybe that didn't exist before in the fish tank existed in the 250 megawatts of deployments? How did you get from the fish tank to that?
So at that time, maybe Foreman and some of those other, if it's okay to mention specific names, but maybe some of them existed at the time, but don't recall them. A lot of it was like for each of these data centers, they built their own local systems to manage. And in this case, using my programming and my engineering, my Linux background, I have some Python experience, Bash experience, I have networking experience, and that's through my studies in high school, through my studies in university, as well as my own hobbies. I partially wrote the system to get one of the first data centers started that we got running. And the first one that we started, we ended up not buying an existing one, we ended up building it. And what I ended up doing was using something like very cheap, but smart switches, cheap so we can save on cost, but smart switches. So we had access to remotely manage the switches and see the MAC tables. We had a system where each port went to a specific physical place. And I wrote a script that could scan the entire network. So even though each machine was DHCP, it had a random IP address. So we couldn't necessarily tell what it is without making a blinking light, which we could do. You can do a blinking light, but when you have 20,000 machines, that takes a long time to find the blinking light, especially when they're actually all blinking in one way or another. These are all S9s at this time. The S9s, they glow green and they have some blinking, right? So finding the right blinking light is not always the best method, or especially when we need to locate a specific device. And so what we did is we created this method. I wrote a script. It would occasionally just run as a batch or what's called a cron job from a local server. And it would scan the network, pull the MAC tables, see what machine, what IP address was connected to what port. Because we physically designed each switch from like port 1 goes to this physical location on the rack. Like this rack, the first position is port number 1. The next one's port number 2. The next one's port number 3. And we go down that shelf. And then the next one in line is like it goes to port number 8. And we go in a specific order. And then the switch names were named after the rack. So if you know the switch name and you know the IP address, you can instantly find it within this list of tables. You know exactly where the miner is. And we did that. And then building on top of that, where the miners had an API exposed, where it would give information about like hash rate or temperature. We built that, plugged it into like open source systems like Grafana. And I don't think it was Prometheus at the time. I can't remember what system backend we used for Grafana, but we used something else. And we used Grafana to graph it. And we basically put this up on large television screens in the NOC or in the monitoring room. And we use that to like monitor the data center both locally and remotely. And this was like built from like a hodgepodge of like different scripts that I wrote and some of the other engineers and software developers wrote. And then eventually, right, you have more unified solutions like Creator that was bought by Brains. You have Foreman and a few others. And there are a few other companies that are now developing some that I probably shouldn't say. But yeah, so
the space has come a long way.
It's come a long way from what it was before, where when we built the data centers back then, like early stages when I was doing the aquarium tanks, to even then in 2017, when we're doing 15, 20 megawatt data centers, it was still like not to the level where it is today. Yeah. And we were kind of like having to like basically hack together a bunch of scripts to make it work.
It makes sense. And obviously it's the progression of the industries, the maturity that you've been able to see throughout your time as a miner. What about negotiating some of these sites and leases and contracts? And what can you talk about back then on how that process worked, and maybe give any details on the difference between negotiating a Bitcoin mining lease or an energy contract as a Bitcoin miner versus a traditional data center, or what some of the things you learned for people that are considering negotiating their own energy contracts that are still applicable today?
A lot of that too, we worked and we empowered and definitely worked very closely. We found local partners to work with. And the reason we did that is local partners are well connected in the community. And that community can include like the utility companies, as well as people that you would need to like hire jobs. So when you're working with government, a lot of like, for example, government workers like approving zoning rights or some permit or regulation, what they like to see is they like to see jobs. This is like a big thing. Another two that we saw, and we saw even early on when we were looking in 2017 at the project in Missoula, is we also have to be careful of, even though a zoning condition may be right, we have to be careful of like sound issues. And this one, like it was actually an industrial zone and there wasn't really much residential. There were a few residential plots in an industrial zone. That's a kind of a thing in of itself. But they also had some other issues where acoustics would bounce off the mountains and you would not hear it in one place, but hear it in another place miles down the road. But then even without those acoustics, you have to think, for example, of how it may affect the local population. So we have to be careful of things like that. For power, when we're doing grid contracts, it's very similar to what a lot of companies do today, in that it forms, like mining typically forms as a base load for power to help secure a stable load of power. As a grid provider, a grid maintainer's job is to maintain supply and demand of power. Both are important. Otherwise, you get blackouts or brownouts. If you have too much power, but not enough demand, you have problems, and vice versa. And so Bitcoin mining runs 24/7, but it can respond with the software on it. It can respond within seconds to changes in supply for power infrastructure that allows grid providers, while working closely with them, to help them balance the grid. So this is a useful application for grid providers. So any of them
what were the
are
early
now
conversations like that? Demand response, implementing demand response with SPI. You guys were one of the first people doing it at enough of a scale where grids like you actually make an impact locally here, running 10, 20 megawatts. So how did those conversations go in the beginning, in the early days?
In the first stages, they had some understanding, but they fully didn't understand it because they didn't see, there's not often many like large industrial users that can like just scale down like Bitcoin mining. For example, other large industrial users that like some Bitcoin miners used to run out of, and some that we actually repurposed, was like an aluminum smelter. An aluminum smelter cannot scale down. You scale down, the aluminum's going to solidify and it's going to ruin your entire factory pretty much, or at least that's my understanding of it. I may be wrong, but that's my understanding. But in other cases, other factories, you have a factory line, you can't just easily scale down. Where Bitcoin mining, it's just a simple command to the firmware on the devices, and you lower the clock frequency of the machines, or in some cases, you cut off power to the machines, and you can basically instantly scale down to meet the power demand, such that like if there is a power plant that goes offline and there's not enough power for the grid, the Bitcoin miner that is taking power from the grid can then scale down their operation. So now there's enough power for residential homes and such so that grid is balanced. And this helps provide a financial incentive because anyone coming in to build extra power for a grid, that whether that's state money, private money, even if it's state money, there needs to be some type of return on investment. And when you have different variable factors to consider and what the cost of power may be, it can be hard to financially model to an investor what their return may be. Or with Bitcoin mining, you can model it for a power contract, you can model it as a very flat rate that the power contract will return. And this provides a very stable modeling for a power utility provider building a plant to model on. And they can model a return on investment and structure that in a right model that fits for their investor profiles. And we worked in educating grid providers. This was difficult in some ways early on. We also worked with a company called Lancium. This was a company that SBA Group invested into. They're based out of Texas. And Lancium started in educating ERCOT about this program. Lancium too, we also did this utilizing wind farms. We were looking at wind farms in West Texas. If you look at kind of wind maps of the United States, where most wind blows and is produced, that area kind of West Texas, I think it's like New Mexico, that rough area of the US produces a lot of wind. But not many people live out there. So you get a high supply of electricity, but a low demand problem. Now you need transmission to transmit all the electricity to like Dallas or Houston or other major population centers. But those transmission lines weren't well built out. And wind farms kept building because they got subsidies from the government. So they would further oversupply power. And this would create a problem because now this is a problem for the power grid maintainers in balancing that supply and demand. So that sometimes the energy prices in West Texas would become negative due to these wind farms. And sometimes they would adjust their fan blades so that they would kind of resist the wind and not flow. And sometimes they would let the wind farms generate electricity anyway. And they were still profitable because they were receiving subsidies from the government.